Right now, somewhere in the universe, a star 20 times more massive than our sun is collapsing. Gravity is crushing its core with a force so extreme that atoms themselves are being destroyed. Protons and electrons are being squeezed together, merged into neutrons, packed so tightly that a single teaspoon of this material would weigh more than 1 billion tons on Earth. By every expectation, this collapse should continue. Gravity should win. The matter should keep falling inward until it vanishes behind an event horizon and becomes a black hole. But it doesn't. Something stops it. Something pushes back against the most violent gravitational collapse in the known universe. And that something comes from one of the strangest and most fundamental laws in all of physics. Before we go any further, if you find these kinds of deep explorations interesting, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. Let's start with the star itself. Because to understand why a neutron star doesn't collapse, you first have to understand what created it. And what created it is one of the most violent events the universe is capable of producing. Imagine a star roughly 8 to 25 times more massive than our sun. A star like this is not gentle. It's not the steady, quiet yellow dwarf that warms our planet and lets life flourish on Earth. A star this massive is a furnace. It burns furiously, pouring out energy at a rate millions of times greater than the sun. It shines so brightly that if you placed it where the sun is, Earth would be uninhabitable, scorched clean of life in an instant. But that ferocious output comes at a cost. The star is burning through its fuel at an extraordinary rate, and because of that, it will live for only a fraction of the time our sun will. While the sun will burn for about 10 billion years, a star 20 times the sun's mass might last only 10 million years. That sounds like a long time by human standards, but by cosmic standards, it's the blink of an eye. The universe is nearly 14 billion years old. A massive star lives for roughly 1,000th of that. It's born, it burns, and it dies in what amounts to a cosmic instant. For most of its life, this star is doing the same thing our sun does. It's fusing hydrogen into helium in its core. This process releases energy because the mass of 4 hydrogen nuclei is slightly more than the mass of 1 helium nucleus. The difference in mass gets converted into energy according to Einstein's famous equation, E equals mc squared. That tiny difference in mass, multiplied by the speed of light squared, produces an enormous amount of energy. This energy creates pressure, outward pressure, radiation pressure and thermal pressure pushing outward in every direction. And this outward pressure is what holds the star up against its own gravity. Gravity wants to pull everything inward, to compress the star down to the smallest possible size. Every atom in the star is being pulled toward the center by the gravitational force of every other atom. The outward pressure from nuclear fusion balances gravity exactly, keeping the star stable. This balance between gravity pulling inward and pressure pushing outward is called hydrostatic equilibrium. It's the same basic principle that keeps every star stable, from the smallest red dwarfs to the most massive blue supergiants. As long as the star can produce energy in its core, the outward pressure holds up against gravity, and the star maintains its size. It's a tug of war, and for millions of years, neither side wins. The star just sits there, burning, shining, balanced. But here's the critical thing. Fusion doesn't produce energy forever. Eventually, the hydrogen in the core runs out. When that happens, the core contracts under gravity because there's no longer enough outward pressure to resist. As the core contracts, it heats up. Gravitational energy is converted into thermal energy, and the temperature rises dramatically. When the core reaches about 100 million degrees, helium begins to fuse into carbon. This new fusion reaction produces energy, restoring the outward pressure, and the star stabilizes again. But this helium fuel lasts for a shorter time than the hydrogen did. The star is burning hotter and faster, consuming each successive fuel in a fraction of the time it took to burn the last. When the helium runs out, the core contracts again, heats up again, and begins fusing carbon into neon and oxygen. This cycle repeats. Each new fuel burns for a shorter time. The star is like a machine running through its gears faster and faster, and each new gear provides less energy than the one before. Let me give you a sense of how dramatic this acceleration is. A star of about 20 solar masses will spend roughly 10 million years burning hydrogen. That's the vast majority of its life. Helium burning lasts about 1 million years. Carbon burning lasts about 1,000 years. Neon burning lasts roughly 1 year. Oxygen burning lasts about 6 months. And silicon burning, the very last stage, lasts about 1 day. 1 single day. The star that spent 10 million years calmly fusing hydrogen burns through its final fuel in 24 hours. The desperation of this process is almost impossible to overstate. The star is running out of options, burning through each new fuel source at an accelerating pace, racing toward a conclusion it cannot avoid. What develops during this process is a layered structure. Picture it like an onion. At the center of the star, the most recently produced element is being fused. Surrounding it is a shell where the previous element is still fusing. Outside that, another shell with an even earlier element. The outermost layers are still mostly hydrogen, the original fuel the star was born with. Near the end of the star's life, you might find iron at the very center, surrounded by a shell of silicon and sulfur, then a shell of oxygen and neon, then carbon, then helium, and finally hydrogen at the surface. Each layer is fusing its own fuel, producing energy, trying to keep the star alive. The whole thing is like a desperately improvised engineering project. The star is doing everything it can to maintain the outward pressure that keeps gravity at bay. But this process has a terminal point, and that terminal point is iron. Iron is element 26 on the periodic table. It has 26 protons and typically 30 neutrons in its most common isotope, and iron is the end of the line for energy-producing nuclear fusion. Here's why. When lighter elements fuse together, the resulting nucleus is more tightly bound than the original nuclei. Binding energy is the energy that holds a nucleus together. When you create a more tightly bound nucleus, the excess energy is released. That released energy is what powers the star. Hydrogen fusing into helium releases energy because helium is more tightly bound. Helium fusing into carbon releases energy because carbon is more tightly bound. This continues all the way up to iron. But iron sits at the very peak of the binding energy curve. It is the most tightly bound nucleus that exists in nature. Nothing is more stable than iron at the nuclear level. This means that fusing iron into heavier elements doesn't release energy. It requires energy. It's an endothermic reaction, meaning it absorbs energy from the star rather than producing it. This is the crucial difference. Every element the star has fused up to this point gave energy back. Hydrogen gave energy, helium gave energy, carbon, neon, oxygen, silicon, all of them gave energy when they fused. But iron doesn't give anything back. Iron is a dead end, a wall. The star has been climbing a staircase of nuclear fusion for millions of years, and iron is the top step. There's nowhere left to go. And this is where the catastrophe begins. The iron core grows larger and larger as silicon fusion continues in the shell surrounding it. More and more iron accumulates in the center of the star. This iron core is incredibly dense and hot, with temperatures exceeding 5 billion degrees. But it's not producing energy. It's just sitting there, supported partly by the intense heat of the core and partly by something called electron degeneracy pressure, a quantum mechanical effect we'll explore in detail shortly. For now, what matters is that this support has limits. The iron core grows until it reaches a critical mass of about 1.4 times the mass of our Sun. This specific limit is called the Chandrasekhar limit, named after the Indian-American astrophysicist Subramanian Chandrasekhar, who calculated it in the early 1930s when he was only about 20 years old. Chandrasekhar showed that when a stellar core exceeds this mass, the quantum mechanical pressure from electrons can no longer hold it up. The calculation was remarkable both for its insight and for the controversy it created. Sir Arthur Eddington, one of the most famous astronomers of the time, publicly ridiculed Chandrasekhar's result, calling it absurd. Eddington couldn't accept that stars could collapse beyond a certain point. But Chandrasekhar was right, and decades later he was awarded the Nobel Prize in Physics for this work. The Chandrasekhar limit represents the maximum mass that can be supported by electron degeneracy pressure. Once the iron core exceeds this limit, the electrons can no longer hold it up. What happens next takes less than a single second. The core collapses, not slowly, not gradually, but catastrophically. The iron core, which at this point is roughly the size of Earth, about 12,000 kilometers across, collapses to a sphere about 20 kilometers across in less than a quarter of a second. Think about that. An object the size of our entire planet crushes itself down to the size of a small city in a fraction of a second. The collapse happens at speeds approaching a quarter of the speed of light, roughly 75,000 kilometers per second. Matter is falling inward so fast that nothing can stop it through ordinary means. The material at the edge of the core is racing toward the center at velocities that would cross the entire Earth in about a tenth of a second. During this collapse, something extraordinary happens at the atomic level. The electrons and protons in the core are squeezed so tightly together that they undergo a process called electron capture, also known as inverse beta decay. Normally, electrons orbit far from the nucleus of an atom. There's an enormous amount of empty space inside an atom. If the nucleus were the size of a marble placed at the center of a football stadium, the nearest electrons would be at the outer walls of the stadium. But during core collapse, that empty space is being crushed out of existence. The electrons are forced into the protons, and they merge together to form neutrons, releasing neutrinos in the process. Each electron-proton merger produces one neutron and one electron neutrino. Enormous numbers of neutrinos are released. In fact, about 99% of the gravitational binding energy released during the entire collapse, roughly 3 times 10 to the 46 joules of energy, escapes in the form of neutrinos. That's more energy than our sun will produce in its entire 10 billion year lifetime, released in a burst lasting just a few seconds. These neutrinos are ghostly particles that barely interact with matter. They pass through the outer layers of the star as if those layers weren't even there. They pass through the Earth as if it weren't there. Trillions of neutrinos from distant supernovae are passing through your body every second, and you don't feel a thing. In 1987, a supernova was observed in the Large Magellanic Cloud, a satellite galaxy of the Milky Way about 168,000 light-years away. Neutrino detectors on Earth picked up a grand total of 25 neutrinos from this event. 25 out of the billions of trillions that washed over our planet. That's how weakly neutrinos interact with matter. And yet, those 25 detections confirmed our understanding of what happens during core collapse. The collapsing core converts most of its protons and electrons into neutrons in a fraction of a second. What was once a ball of iron atoms, with their orderly structure of protons, neutrons, and electrons, becomes a ball of almost pure neutrons, packed together at incredible density. The density of this neutron core is staggering. We're talking about roughly 200 million metric tons per cubic centimeter. Let me try to make that tangible. A sugar cube of this material would weigh about as much as all of humanity combined. A teaspoon would outweigh the entire population of Earth, multiplied by about 30. Every building, every ship, every vehicle, every object ever constructed by human civilization, and all of it together would weigh less than a thimbleful of neutron star material. The matter is compressed to the point where individual neutrons are essentially touching. The spacing between particles in ordinary matter, which is mostly empty space inside atoms, has been eliminated. The empty space that makes up 99.9999% of every atom has been crushed out of existence. Now, here's what's remarkable. When the collapsing core reaches nuclear density, roughly the density of an atomic nucleus itself, something stops the collapse. The core bounces. It actually rebounds slightly, like a rubber ball that's been compressed beyond its natural limit. The infalling material hits the suddenly rigid core and bounces back. This bounce sends a shockwave outward through the still infalling outer layers of the star. The shockwave is extraordinarily powerful. It carries an immense amount of energy, but it initially stalls. It loses energy as it plows through the dense material still raining down from above, material that doesn't know the core has already bounced and is still falling inward at enormous speed. For a brief moment, the explosion hangs in the balance. The shockwave has stalled, losing energy faster than it can push outward. If nothing else happens, the shockwave will fade, the outer layers will fall onto the core, and a black hole will form with no explosion at all. But this is where the neutrinos make their crucial contribution. The flood of neutrinos streaming out from the collapsed core deposits a tiny fraction of its energy into the material just behind the stalled shockwave. Less than 1% of the total neutrino energy is absorbed, but even that tiny fraction represents an enormous amount of energy. It's enough to revive the shockwave and send it blasting outward through the rest of the star. The result is a core collapse supernova, one of the most powerful explosions in the universe. For a few weeks, a single supernova can outshine an entire galaxy of hundreds of billions of stars. The total energy of the explosion is about 10 to the 44 joules in kinetic energy alone, and about 100 times more than that in neutrinos. The outer layers of the star are blown into space at speeds of 15,000 to 40,000 kilometers per second. These layers carry with them heavy elements forged in the star's core and in the explosion itself. Elements like carbon, oxygen, silicon, iron, gold, platinum, and uranium. These elements are scattered into the surrounding interstellar medium, enriching the gas and dust from which new stars and planets will eventually form. This is where the atoms in your body came from. Every atom of iron in your blood, every atom of calcium in your bones, every atom of oxygen you breathe was forged in a star like this and scattered by a supernova explosion billions of years ago. The carbon in your cells was fused from helium in the core of a massive star. The gold in your jewelry was created in the extreme conditions of a supernova shockwave, or perhaps in the collision of two neutron stars. You are quite literally made of star stuff. The atoms in your left hand may have come from a different star than the atoms in your right hand. You are a collection of matter that has been recycled through multiple generations of stars, each one living and dying and scattering its enriched material into space to be incorporated into the next generation. But when the explosion clears, when the expanding debris is racing outward into interstellar space at thousands of kilometers per second, something remains behind at the center. The core, that ball of neutrons, roughly 20 kilometers across, containing more mass than our entire sun, compressed into a volume smaller than a city. This is a neutron star, and this is where our real question begins. Because by all rights, this object shouldn't exist. Not as a stable structure. Consider what we're dealing with. The mass of roughly 1.5 suns, sometimes even 2 suns, packed into a sphere about 20 kilometers in diameter. The gravitational field at the surface is beyond anything else in the observable universe outside a black hole. To leave the surface, you'd need to be traveling at 1/3 the speed of light. If you dropped a pebble from a height of 1 meter above the surface, it would hit the surface traveling at about 7 million kilometers per hour. That's not a typo. 7 million kilometers per hour from a drop of 1 meter. The tidal forces near the surface are so extreme that nothing could survive the approach. Long before you touch the surface, the difference in gravitational pull across the length of your body would overwhelm every chemical bond holding you together. You wouldn't just be crushed on a neutron star. You'd be stretched into a thread of individual atoms. Physicists call this spaghettification, and it's not a metaphor. It's a literal description of what gravity does to matter near these objects. And yet, somehow, this impossibly dense object doesn't keep collapsing. Gravity should win here. The gravitational force is immense. The mass is enormous. By any intuitive reckoning, this matter should just keep falling inward, compressing further and further, until it forms a black hole. That's what gravity does. It pulls things together. And here it's pulling with more force than almost anywhere else in the universe. But the collapse stops. Something pushes back. Something resists the most extreme gravitational compression in the observable cosmos outside of a black hole. That something is not heat. A newly formed neutron star is incredibly hot. with internal temperatures that can reach hundreds of billions of degrees in the first seconds after formation. But the neutron star will eventually cool. Over thousands and millions of years, it will radiate away its heat. And when it does, it won't collapse. The thing holding it up doesn't depend on temperature. It's not radiation pressure. There's no nuclear fusion occurring in the core of a neutron star. There's no energy source generating outward radiation pressure. The fuel is spent. The nuclear reactions are over. It's not the ordinary mechanical strength of matter. No material in the universe is strong enough to resist the gravitational force at the surface of a neutron star. Steel, diamond, carbon nanotubes, every material we've ever created or discovered would be crushed instantaneously under these conditions. Material strength is completely irrelevant here. What holds up a neutron star is something deeper, something quantum mechanical, something that comes from the fundamental nature of the particles themselves. The neutrons inside the star are fermions, and fermions obey a rule so absolute, so inviolable, that it can resist the crushing weight of a sun and a half packed into a ball smaller than Manhattan. This rule doesn't bend, it doesn't weaken, it doesn't depend on temperature or pressure or any environmental condition. It's woven into the mathematical structure of quantum mechanics itself, and it creates a pressure and outward force that has nothing to do with heat or motion in the classical sense. A force that exists purely because of how the universe requires certain particles to behave. To understand this force, to understand why a neutron star can defy the most extreme gravity in the known universe without collapsing, we need to leave the world of dying stars and exploding supernovae for a moment. We need to go deeper, down to the level of individual particles, down to the quantum world where the rules are different from anything our everyday experience prepares us for. Because the answer to why neutron stars don't collapse lies not in the stars themselves, but in the fundamental quantum nature of the matter they're made of. To understand what holds up a neutron star, you need to understand something about the fundamental nature of matter that isn't obvious from everyday experience. In our world, objects follow predictable, intuitive rules. If you push something, it moves. If you compress something, it gets smaller. If you squeeze hard enough, things eventually break. You can always, it seems, make things more compact if you apply enough force, but at the subatomic level, matter follows different rules that seem strange and counterintuitive, rules that sometimes appear to defy common sense entirely. And yet these rules have been confirmed by over a century of experiments with extraordinary precision. They are among the most rigorously tested ideas in the entire history of science. These are the rules of quantum mechanics, and one rule in particular is responsible for holding up neutron stars against gravity. But before we get to that rule, we need to understand something about particles themselves, because not all particles are the same. In fact, every particle in the universe falls into one of exactly two categories. No exceptions. No particles that straddle the line. Every particle that exists, every particle that has ever existed or ever will exist, belongs to one of two fundamental families. These families are called fermions and bosons. And the distinction between them is one of the most important in all of physics. It determines how particles behave, how they interact, what kinds of structures they can form, and ultimately, whether or not a dead star collapses into a black hole. Fermions include particles like electrons, protons, and neutrons. These are the particles that make up ordinary matter. Everything you can touch, see, hold, or stand on is made of fermions. Your body is made of atoms, and atoms are made of protons, neutrons, and electrons. All fermions. The chair you're sitting in, the ground beneath your feet, the air you breathe, the screen or speaker. Delivering these words to you right now, all of it is built from fermions. Fermions are also distinguished by a quantum property called spin. Every fermion has a half-integer spin, meaning its intrinsic angular momentum comes in values like 1/2, 3/2, 5/2, and so on, measured in units of the reduced Planck constant. Electrons, protons, and neutrons all have a spin of 1/2. This spin value isn't something the particle chooses. It's built into the particle's identity as fundamental as its mass or its electric charge. Bosons are the other family. They include particles like photons, which are particles of light, and gluons, which carry the strong nuclear force that holds atomic nuclei together. The W and Z bosons carry the weak nuclear force responsible for certain types of radioactive decay. And the Higgs boson, famously discovered at the Large Hadron Collider in 2012, is responsible for giving other particles their mass. Bosons have integer spin values 0, 1, 2, and so on. The photon has a spin of 1. The Higgs boson has a spin of 0. Gravitons, if they exist, would have a spin of 2. This integer spin is what defines them as bosons. Now here's the difference that matters. The difference that determines the fate of dead stars. Bosons are, for lack of a better word, social. They're perfectly happy to pile on top of each other. You can put as many bosons as you want into the exact same quantum state, and they don't care. In fact, bosons actually prefer to be in the same state. They're attracted to occupied states. This is a quantum mechanical phenomenon called Bose-Einstein statistics, and it leads to some remarkable effects. It's how lasers work. In a laser, millions upon millions of photons are all in exactly the same quantum state, all with the same energy, the same frequency, the same direction, the same phase. They move together in perfect lockstep, producing coherent light. This is only possible because photons are bosons and can all occupy the same state simultaneously. It's also why Bose-Einstein condensates exist. When you cool certain atoms to temperatures very close to absolute zero, the atoms can all drop into the same quantum ground state, creating a single macroscopic quantum object. Thousands or millions of atoms behaving as one entity. This only works because at very low temperatures, certain atoms behave as composite bosons. Superfluidity and superconductivity are related phenomena. In a superfluid, atoms flow with zero viscosity, no friction whatsoever. In a superconductor, electrons pair up into composite bosons called Cooper pairs and conduct electricity with zero resistance. All of these phenomena arise because bosons can share quantum states without limit. But fermions are different. Profoundly, fundamentally, uncompromisingly different. Fermions are antisocial. They absolutely refuse to share the same quantum state with another identical fermion. This isn't a preference or a tendency. It's not something that happens most of the time with occasional exceptions. It's an absolute inviolable law of nature with no exceptions whatsoever. It has never been violated in any experiment ever conducted. It cannot be violated. The mathematical structure of quantum mechanics makes it impossible. This law is called the Pauli exclusion principle. It was discovered by the Austrian physicist Wolfgang Pauli in 1925, and it earned him the Nobel Prize in Physics in 1945. Pauli was trying to explain why the electrons in an atom arrange themselves in distinct shells rather than all collapsing into the lowest energy state. He realized that something was preventing the electrons from all occupying the same state, that something turned out to be a fundamental property of all fermions, a rule built into the mathematical framework of quantum field theory itself. The Pauli exclusion principle states that no two identical fermions can occupy the same quantum state simultaneously. Let me unpack what that means. A quantum state is defined by a set of quantum numbers, essentially a collection of labels that describe everything about a particle's condition: its energy, its momentum, its position in a particular sense, its spin orientation. For an electron in an atom, the quantum state is defined by 4 quantum numbers: the principal quantum number, which determines the energy level; the angular momentum quantum number, which determines the shape of the orbital; the magnetic quantum number, which determines the orientation of the orbital; and the spin quantum number, which can be either +1/2 or -1/2. The Pauli exclusion principle says that no two electrons in the same atom can have the same values for all 4 quantum numbers. They must differ in at least one. This is why electron shells fill up. The lowest energy level can hold only 2 electrons, one with spin up and one with spin down. Once those 2 states are occupied, any additional electron must go into a higher energy level. This is the foundation of all chemistry. It's why the periodic table has the structure it does. It's why different elements have different properties. It's why some elements are metals and others are gases. It's why carbon can form the complex bonds that make life possible. Now here's what makes the Pauli exclusion principle so remarkable. If you try to force 2 identical fermions into the same quantum state, you can't. Not because there's a physical barrier in the traditional sense, not because they bounce off each other like billiard balls, not because some force pushes them apart. The reason is more profound than that. The probability of finding 2 identical fermions in exactly the same quantum state is precisely 0. Not approximately 0, not effectively 0. Not 0 for all practical purposes. Exactly, mathematically, perfectly 0. The wave function that describes 2 identical fermions in the same state is identically 0 everywhere. It doesn't exist. The universe doesn't allow it. It's as forbidden as 2 + 2 = 5. It's not that it's unlikely. It's that it's logically impossible within the mathematical framework that governs reality. This arises from a deep mathematical property of fermions. The wave function describing a system of identical fermions must be antisymmetric. This means that if you swap 2 identical fermions, the wave function changes sign. It goes from positive to negative, or negative to positive. Now, if 2 fermions are in exactly the same state, swapping them changes nothing because they're identical and in the same state. But the antisymmetry requirement says the wave function must change sign. The only mathematical function that is equal to its own negative is 0. So the wave function must be 0, meaning the probability of that configuration is 0. It simply cannot happen. This might sound abstract, like a mathematical curiosity with no practical consequences. But the consequences are enormous. The Pauli exclusion principle is responsible for the structure of all matter. Without it, every electron in every atom would collapse into the lowest energy state. All atoms would behave identically. There would be no chemistry, no molecules, no solids, no liquids, no diversity of materials whatsoever. The periodic table would not exist. Carbon would behave the same as oxygen, which would behave the same as iron. Life would be impossible. Structure of any kind would be impossible. The reason matter has volume, the reason your hand doesn't pass through the table when you rest it there, is ultimately due to the Pauli exclusion principle. The electrons in the atoms of your hand and the electrons in the atoms of the table are all fermions. When you push your hand against the table, the electrons in both objects resist being compressed into the same quantum states. This creates a repulsive force, a quantum mechanical pressure that you perceive as solidity. Every time you touch anything, you're feeling the Pauli exclusion principle at work. Now let's connect this to what happens inside collapsed stellar objects. Because the Pauli exclusion principle doesn't just determine the structure of atoms, it determines the fate of dead stars. Think about what happens when you compress a collection of fermions into a smaller and smaller volume. Quantum mechanics tells us that particles behave like waves. Each fermion has an associated wavelength called the de Broglie wavelength, which is related to the particle's momentum. Higher momentum means shorter wavelength. Lower momentum means longer wavelength. These waves must fit within the space available to them. If you confine a particle to a smaller region of space, its wave must have a shorter wavelength, which means higher momentum, which means higher energy. This is closely related to the Heisenberg uncertainty principle, which states that the more precisely you know a particle's position, the less precisely you can know its momentum, and vice versa. Confining a particle to a small space is equivalent to knowing its position precisely, which means its momentum must be uncertain over a wide range. That wide range of momentum means some particles must have very high momenta. Now combine this with the Pauli exclusion principle. You have a collection of identical fermions, say neutrons, crammed into a small volume. The lowest energy quantum states fill up first because fermions naturally seek the lowest available energy. The first neutron settles into the ground state, the lowest possible energy. The second neutron takes the next lowest state, and so on. But as you keep adding neutrons or keep compressing the volume, the low energy states fill up. Because no two identical fermions can share a state, each additional neutron must go into a progressively higher energy state. The last neutrons to find states are forced into very high energy levels. These high energy fermions have high momenta, and particles with high momenta exert pressure on their surroundings. They push outward. This is degeneracy pressure. It's a quantum mechanical pressure that arises purely from the Pauli exclusion principle, combined with the confinement of fermions. It has nothing to do with temperature, nothing to do with thermal motion, nothing to do with any energy generating process. It exists because fermions refuse to share quantum states. And when you compress them, you force them into higher and higher energy states, and those high energy fermions push back. Let me emphasize how fundamentally different this is from ordinary pressure. The pressure inside a balloon comes from the thermal motion of gas molecules. Heat the gas and the molecules move faster, hitting the walls of the balloon harder, increasing the pressure. Cool the gas and the molecules slow down, reducing the pressure. At absolute zero, If you could cool a classical gas to zero temperature, the pressure would be zero. The molecules would stop moving entirely. But degeneracy pressure doesn't work this way. Even at absolute zero, with no thermal energy whatsoever, degeneracy pressure exists. It persists. It doesn't diminish as the temperature drops. You could cool a collection of fermions to the coldest temperature the laws of physics allow, and the pressure from the Pauli exclusion principle would remain exactly the same. This is because degeneracy pressure isn't generated by thermal motion. It's generated by the quantum mechanical requirement that fermions cannot share states. Even at zero temperature, the fermions are still occupying distinct quantum states. And if they're compressed tightly enough, the highest occupied states have enormous energy and momentum. This is not a theoretical curiosity. Degeneracy pressure is what keeps every white dwarf star in the universe from collapsing. And understanding how it works in white dwarfs is the key to understanding how it works in neutron stars. A white dwarf is the remnant of a star like our Sun. Stars between roughly 1 and 8 solar masses don't die in supernova explosions. They die more gently. When such a star exhausts the hydrogen in its core, it goes through some of the same stages as a massive star, fusing helium into carbon and oxygen, but it's not massive enough to reach the temperatures needed to fuse carbon. The core stalls at carbon and oxygen. The outer layers of the star are gently expelled into space, forming a beautiful glowing shell of gas called a planetary nebula. What remains behind is the exposed core, a ball of carbon and oxygen roughly the size of Earth, but containing about the mass of our Sun. No nuclear fusion is occurring in this core. There's no energy being produced, no thermal pressure being generated. So what holds the white dwarf up against gravity? The answer is electron degeneracy pressure. The electrons in the white dwarf are packed to extreme densities. The typical density of a white dwarf is about 1 million grams per cubic centimeter. A teaspoon of white dwarf material would weigh about 5 metric tons on Earth. At these densities, the electrons are forced into high-energy quantum states by the Pauli exclusion principle. These high-energy electrons exert tremendous outward pressure, enough to balance the inward pull of gravity. The remarkable thing about a white dwarf is its long-term stability. It has no energy source, it's not burning any fuel, it's simply sitting in space, slowly radiating away its residual heat, getting dimmer and cooler over time. A newly formed white dwarf might have a surface temperature of over 100,000 degrees, glowing brilliant blue-white. Over billions of years it cools to tens of thousands of degrees, then thousands, then eventually it will become a cold, dark object, sometimes called a black dwarf. But this cooling takes longer than the current age of the universe, so no black dwarfs exist yet. The universe is simply not old enough. The key point is that as the white dwarf cools, the electron degeneracy pressure doesn't change. The pressure isn't coming from heat. It's coming from the quantum nature of the electrons. Even as the temperature drops towards zero, the electrons are still occupying high-energy quantum states, because the Pauli exclusion principle forces them to. The white dwarf remains structurally stable regardless of its temperature. It will never collapse due to cooling. But there is a limit. Subramanian Chandrasekhar's great insight, the one that Arthur Eddington so wrongly mocked, was to calculate what happens to electron degeneracy pressure as a white dwarf becomes more massive. As mass increases, the gravitational compression increases. The electrons are squeezed into ever smaller volumes, forced into higher and higher energy states. At some point, the electrons are moving so fast that they approach the speed of light. They become relativistic. And this is where everything changes. In the non-relativistic regime, when electrons are moving well below the speed of light, there's a straightforward relationship between compression and pressure. Squeeze the electrons into half the volume, and the pressure increases by a predictable amount. The pressure rises steeply with compression, steep enough to always stay ahead of gravity. But once the electrons become relativistic, once they're moving close to the speed of light, the relationship changes. The pressure still increases with compression, but more slowly. It no longer rises steeply enough to outpace gravity. The mathematics shows that in the ultra-relativistic limit, the pressure grows as the 4/3 power of the density, while gravity grows faster than that for increasing mass. There's a crossover point, a critical mass, beyond which gravity will always win. That critical mass is the Chandrasekhar limit, approximately 1.4 solar masses. Below the Chandrasekhar limit, electron degeneracy pressure is sufficient. The white dwarf is stable. It will persist forever, cooling gradually, never collapsing. Above the Chandrasekhar limit, electron degeneracy pressure fails. The electrons are moving at nearly the speed of light, but the pressure they generate can no longer keep up with gravity. The star collapses. This is precisely what happens during the formation of a neutron star. The iron core of a massive star exceeds the Chandrasekhar limit, electron degeneracy pressure fails, and the core collapses. But during the collapse, the electrons are forced into the protons, creating neutrons. And now, we have a new situation. Instead of a ball of electrons and nuclei, we have a ball of almost pure neutrons. And neutrons are also fermions. They also obey the Pauli exclusion principle. They also generate degeneracy pressure when compressed. But neutrons are fundamentally different from electrons in one crucial way. They are much more massive. A neutron is about 1,836 times heavier than an electron. This mass difference is enormously important. A particle's de Broglie wavelength is inversely proportional to its momentum. For a given kinetic energy, a heavier particle has a larger momentum and therefore a shorter wavelength. This means neutrons can be packed into a much smaller volume before their wavelengths start overlapping, and the exclusion principle kicks in at its strongest. More importantly, because neutrons are heavier, they reach relativistic speeds at much higher densities than electrons do. An electron becomes relativistic at white dwarf densities, about 1,000,000 grams per cubic centimeter. A neutron doesn't become relativistic until densities hundreds of millions of times higher. This means neutron degeneracy pressure can operate effectively at densities far beyond where electron degeneracy pressure fails. This is why neutron stars can exist. Electron degeneracy pressure failed at 1.4 solar masses, but the collapse that followed created a new configuration, a ball of neutrons at nuclear density where neutron degeneracy pressure takes over. The neutrons are now the fermions resisting compression. They're packed at densities of hundreds of millions of metric tons per cubic centimeter, and the Pauli exclusion principle forces them into high-energy quantum states, generating an enormous outward pressure. This pressure is sufficient to hold the collapse and support the weight of the star. But neutron degeneracy pressure isn't the only force at work. At the incredible densities inside a neutron star, the strong nuclear force between neutrons also plays a critical role. The strong force is the force that holds atomic nuclei together. It binds protons and neutrons into nuclei, overcoming the electromagnetic repulsion between the positively charged protons. At relatively large distances between neutrons, say a few femtometers, the strong force is attractive. It pulls neutrons toward each other. This is what holds nuclei together. But at very short distances, below about 0.7 femtometers, the strong force becomes intensely repulsive. It pushes the neutrons apart. This repulsive core of the nuclear force acts as a hard wall that prevents neutrons from overlapping. Inside a neutron star, the neutrons are packed so tightly that the repulsive component of the nuclear force becomes significant. It adds to the degeneracy pressure, providing additional support against gravity. The combination of neutron degeneracy pressure and nuclear force repulsion together creates enough outward force to balance the inward pull of gravity and stabilize the neutron star. The relative contributions of these two effects, degeneracy pressure and nuclear force, depend on the density. At lower densities, near the outer parts of the neutron star, degeneracy pressure dominates. At the highest densities in the core, where neutrons are packed even more tightly, the nuclear force repulsion becomes increasingly important. The exact balance between these contributions is one of the central questions in nuclear astrophysics. It's encoded in what physicists call the equation of the state of dense matter, a mathematical relationship that tells you how much pressure a given density of matter produces. Different theoretical models of the nuclear force give different equations of state, and which one is correct determines many of the observable properties of neutron stars, including how large they are, how massive they can become, and ultimately where the boundary between neutron stars and black holes lies. Let me pause here and make sure the fundamental concept is clear, because this is the heart of the entire story. A neutron star is held up against gravity by a quantum mechanical effect. The Pauli exclusion principle acting on neutrons generates a pressure that doesn't depend on temperature, doesn't require any energy source, and doesn't diminish over time. This pressure, supplemented by the repulsive component of the strong nuclear force at very short distances, balances the enormous gravitational force that would otherwise crush the star into a black hole. This is quantum mechanics operating on a cosmic scale. A law discovered by studying the behavior of electrons inside atoms, a principle that governs things smaller than a billionth of a meter, is responsible for the structural stability of objects 20 kilometers across containing more mass than our Sun. The same principle that determines why gold is yellow and copper is reddish, why diamond is hard and graphite is soft, why certain elements are chemically reactive and others are inert. This same principle prevents the most extreme gravitational collapse short of a black hole. It operates at every scale. In the atoms of your fingertip, it's the reason the tip of your finger doesn't pass through whatever you touch. In a white dwarf, it supports a solar mass against gravity for billions of years. In a neutron star, it holds up 1.5 solar masses at nuclear density. The principle is the same everywhere. Only the fermions and the scale are different. Electrons in atoms, electrons and white dwarfs, neutrons and neutron stars. The same exclusion principle applied to different particles at different densities, creating structure and stability across an extraordinary range of conditions. And there's something almost poetic about this. The universe builds structure through a prohibition, not through a force that actively pushes in the way a spring pushes back when compressed, but through a fundamental refusal. Fermions refuse to be identical. They refuse to occupy the same quantum state. And from that refusal, that quiet quantum stubbornness, emerges the rigidity of matter, the structure of atoms, the chemistry of life, and the stability of the densest objects in the cosmos. It's a prohibition that builds worlds, but every prohibition has its limits. Every balance can be broken, and the balance inside a neutron star, extraordinary as it is no exception. Because gravity never stops, it never tires, it never gives up, it just keeps pulling. And if enough mass accumulates, if the gravitational force becomes strong enough, then even the Pauli exclusion principle, even the nuclear force, even the combined quantum mechanical resistance of trillions upon trillions of neutrons packed at nuclear density, all of it can be overwhelmed. And when that happens, nothing in the known laws of physics can prevent what comes next. Now that we understand the forces at play, let's examine what this balance actually looks like inside a neutron star. Because the equilibrium between gravitational compression and neutron degeneracy pressure creates an object unlike anything else in the known universe. An object so extreme in every measurable property that it pushes the boundaries of what we thought matter could do. An object that is, in a very real sense, a single atomic nucleus the size of a city. In an ordinary atomic nucleus, protons and neutrons are held together by the strong force at densities of about 230 million metric tons per cubic centimeter. That's already an extraordinary density. If you could somehow gather a cubic centimeter of pure nuclear matter, it would weigh more than every supertanker ship on Earth combined. But a nucleus is tiny. A few femtometers across. A quadrillionth of a meter. You'd need to line up roughly 10 trillion nuclei end to end to span a single centimeter. A neutron star takes that same density and extends it across kilometers. Not femtometers. Kilometers. The entire object, roughly 20 kilometers from one side to the other, is at nuclear density or beyond. It's as if someone took an atomic nucleus and inflated it by a factor of about 10 trillion, preserving the density while scaling up the size. That's what a neutron star is. A nucleus the size of a city, the largest nucleus in existence. The balance that holds this structure stable is conceptually the same as the balance in any star, but expressed through completely different physics. In a normal star like the Sun, the outward push comes from thermal pressure generated by nuclear fusion. The core fuses hydrogen, releases energy, and that energy heats the gas, creating pressure that resists gravity. If something causes the core to produce more energy, the star expands slightly, which cools the core, which reduces the energy output, which causes the star to contract back. If something causes the core to produce less energy, the star contracts, which heats the core, which increases the energy output, pushing the star back out. This feedback loop, this self-correcting mechanism, keeps the star in equilibrium for millions or billions of years. In a neutron star, the physics is different, but the principle is analogous. The outward push comes from degeneracy pressure and nuclear forces. These pressures don't depend on temperature, which is important. A neutron star doesn't need an ongoing energy source to remain stable. It doesn't need fuel. It doesn't need fusion. The equilibrium is maintained by the fundamental quantum nature of the matter itself. If something were to compress the neutron star slightly, the neutrons will be pushed into higher energy states, increasing the degeneracy pressure and pushing back. If something were to cause the star to expand slightly, the degeneracy pressure would decrease, allowing gravity to pull it back in. The star finds this equilibrium point and stays there, not because of an energy-generating feedback loop, but because of the intrinsic resistance of fermions to being compressed beyond a certain point. This equilibrium creates a structure with distinct layers, each with its own remarkable properties. Let's start at the surface and work our way inward. Picture yourself descending into a neutron star, layer by layer, moving from the comparatively familiar toward the profoundly exotic. The outermost layer is the atmosphere. It's incredibly thin, perhaps only a few centimeters to a few meters thick. But don't let that thinness fool you into thinking it's insignificant. The surface gravity is so overwhelmingly strong that even this thin atmospheric layer is compressed to extraordinary densities. The matter here is ionized plasma, atoms that have been stripped of their electrons by the intense heat. A newly formed neutron star might have a surface temperature of about 1 million degrees or more. The composition of the atmosphere depends on what has fallen onto the neutron star from its surroundings. It might be hydrogen, helium, or heavier elements accreted from a companion star, or from the debris of the original supernova. Light emitted from this atmosphere carries crucial information. By analyzing the spectrum of this light, astronomers can determine the surface temperature, composition, and even the strength of the gravitational field. Below the atmosphere lies the outer crust. This region extends from the surface down to a depth of a few hundred meters, though the exact thickness depends on the neutron star's mass and equation of state. The density here ranges from about 1 million grams per cubic centimeter at the top, comparable to a white dwarf, to about 400 billion grams per cubic centimeter at the bottom. In this region, matter is arranged in a crystalline lattice, similar in concept to the regular arrangement of atoms in a metal on Earth, but under conditions that are vastly more extreme. The nuclei are arranged in an orderly pattern, locked into position by the enormous pressure. Free electrons flow through this lattice, making the outer crust an excellent conductor of electricity and heat. The magnetic field of the neutron star threads through this crust, anchored to it. If the crust shifts or cracks, the magnetic field configuration changes, which can produce observable effects. The outer crust is actually the most well-understood part of a neutron star, because the densities here, while extreme, are within the range that nuclear physics can model with reasonable confidence. We know what atomic nuclei look like at these densities. They're iron group elements at the surface, progressively more neutron-rich nuclei as you go deeper. As the pressure increases with depth, it becomes energetically favorable for nuclei to capture electrons, converting protons into neutrons. The nuclei become heavier and more bloated with neutrons as you descend. This process of electron capture is gradual, but it changes the character of the matter profoundly as you move deeper into the crust. At a density of about 400 billion grams per cubic centimeter, something remarkable happens. You cross the neutron drip line. This is the point at which the nuclei have absorbed so many neutrons that they literally cannot hold anymore. Neutrons begin to leak out of the nuclei, dripping free and floating in the spaces between them. Below this point, in the inner crust, you have a mixture of extremely neutron-rich nuclei surrounded by a sea of free neutrons and a background of electrons. The free neutrons outnumber the neutrons bound inside nuclei. You're now in a regime that has no analog anywhere else in the universe, except possibly in the moments during a supernova collapse or in the collisions of neutron stars. This material cannot exist under normal conditions. It exists only because of the crushing pressure. And the free neutrons in the inner crust do something extraordinary. They form a superfluid. At these temperatures and densities, neutrons pair up through the strong nuclear force, forming what are called Cooper pairs, analogous to how electrons pair up in a superconductor. These paired neutrons behave as composite bosons, and bosons, as we discussed, can all occupy the same quantum state. The result is a superfluid, a state of matter that flows with zero viscosity. No friction, no resistance. If you could somehow stir a superfluid, it would keep spinning forever, never slowing down. Superfluidity in neutron stars is not theoretical speculation. It has been confirmed observationally. Occasionally, a pulsar's rotation rate suddenly increases in an event called a glitch. The leading explanation for these glitches involves the superfluid interior. The superfluid neutrons, which rotate by forming tiny quantized vortices, can be spinning at a slightly different rate than the solid crust. When the crust slows down gradually due to magnetic braking, the difference in rotation between the crust and the superfluid interior builds up. Eventually, vortices in the superfluid unpin from the crust and transfer angular momentum to it, causing a sudden spin-up. The crust lurches forward in a rotation. We detect this as a glitch. These glitches have been observed in hundreds of pulsars, and their properties match the predictions of superfluidity models remarkably well. Deeper still, below the inner crust at densities exceeding nuclear density, roughly 230 million metric tons per cubic centimeter, you enter the outer core. This is where things get truly extreme. The nuclei that persisted in the crust have completely dissolved. There are no more discrete nuclear structures. Instead, the matter is a uniform fluid of predominantly neutrons with a small admixture of protons and electrons. About 95% neutrons, roughly 5% protons, and a matching number of electrons to maintain electrical neutrality. This region makes up most of the neutron star's volume and most of its mass. Both the neutrons and the protons in the outer core are in superfluid states. The neutrons form a superfluid, just as in the inner crust. The protons also form Cooper pairs and become both superfluid and superconducting. Superconductivity means they can carry electrical current with absolutely zero resistance. This superconducting proton fluid is responsible for sustaining and shaping the neutron star's magnetic field. In an ordinary conductor, electrical currents decay over time because of resistance. But in a superconductor, currents persist indefinitely. This is why neutron stars can maintain extremely powerful magnetic fields for millions and billions of years. The currents that generate those fields never dissipate because the proton fluid has zero electrical resistance. And then there's the inner core, the very center of the neutron star. And this is where our understanding reaches its frontier. The density in the inner core can reach 5 to 10 times nuclear density. These are conditions that don't exist anywhere else in the observable universe, at least not in any stable, long-lived object. We cannot reproduce these conditions in any laboratory on Earth. Even the most powerful particle accelerators, machines like the Large Hadron Collider that can briefly produce temperatures exceeding several trillion degrees, cannot sustain the extreme densities found in the inner core of a neutron star. Temperature and density are different things. And while accelerators excel at creating extreme temperatures, they cannot create the sustained compression found inside a neutron star. This means we genuinely don't know what the matter in the inner core looks like. Several theoretical possibilities have been proposed, each fascinating, each radically different from ordinary matter. One possibility is that at these extreme densities, neutrons themselves break apart. Neutrons are not fundamental particles. Each neutron is composed of 3 quarks, 2 down quarks, and 1 up quark, held together by gluons. Under sufficient pressure, the boundaries between individual neutrons might dissolve, allowing the quarks to roam freely. This state of matter is called a quark-gluon plasma, and it represents a phase transition as dramatic as ice melting into water, but at an incomparably higher energy scale. In a quark-gluon plasma, the quarks are no longer confined inside individual neutrons. They form a continuous sea of quarks and gluons. Another possibility involves strange quarks. Ordinary matter contains only up quarks and down quarks, but there's a third type of light quark called the strange quark. Under extreme pressure, some of the up and down quarks might convert into strange quarks. If this happens, the core could contain strange quark matter, a roughly equal mixture of up, down, and strange quarks. Some theorists have even proposed that strange quark matter might be the true ground state of matter, meaning that if you could compress ordinary matter enough to trigger the transition, the strange quark matter would be more stable than ordinary nuclear matter. If this is true, then entire stars could potentially be made of strange quark matter. These hypothetical objects are called strange stars, and they would look similar to neutron stars from the outside, but would have subtly different properties. Yet another possibility involves exotic particles called hyperons. Hyperons are baryons like neutrons and protons, but contain 1 or more strange quarks. Under sufficient pressure, it might become energetically favorable for some neutrons to convert into hyperons. The presence of hyperons would soften the equation of state, reducing the pressure at high densities. This creates what nuclear physicists call the hyperon puzzle. If hyperons appear at high density, they reduce the maximum mass a neutron star can support. But we've observed neutron stars with masses above 2 solar masses, which many hyperon models struggle to accommodate. Either hyperons don't appear as readily as some models predict, or there's some additional repulsive interaction at high density that compensates for their softening effect. Still, other models propose the formation of a Bose-Einstein condensate of pions or kaons, subatomic particles that would emerge at extreme densities and form a collective quantum state. Each of these possibilities represents a different equation of state, a different relationship between density and pressure. And the equation of state is the single most important unknown in neutron star physics because it determines everything. The size of the neutron star, its maximum possible mass, the thickness of its crust, the frequency of its oscillation modes, the gravitational waves it emits when disturbed, even the details of what happens when two neutron stars collide. Determining the correct equation of state is one of the great ongoing projects in modern astrophysics and nuclear physics. Every observation of a neutron star provides a clue. Measuring a neutron star's mass constrains the equation of state because the star must be able to support that mass. Measuring a neutron star's radius constrains it further because the radius depends directly on how much the matter can be compressed. Observations of neutron star cooling rates, pulsar glitches, gravitational waves from neutron star mergers, all of these provide pieces of the puzzle. Slowly, observation by observation, the range of possible equations of state is being narrowed. We don't yet know the answer, but we're closer than we've ever been. Now let's step back from the internal structure and talk about what neutron stars are like as physical objects. Because the numbers associated with these objects are so extreme that they strain our ability to comprehend them. Every measurable property of a neutron star is pushed to some kind of limit. Size, density, gravity, rotation, magnetic field. In every category, neutron stars are among the most extreme objects in the cosmos. A typical neutron star has a mass between about 1.4 and 2.2 times the mass of our Sun. Some may be slightly less massive. A few are heavier still, with the most massive confirmed examples exceeding 2.3 solar masses. The Sun itself has a mass of about 2 nonillion kilograms. That's a 2 followed by 30 zeros. A neutron star contains all of that mass, often more, compressed into a sphere roughly 20 kilometers across. For comparison, the Sun has a diameter of about 1.4 million kilometers. A neutron star takes all that mass and compresses it by a factor of roughly 70,000 in diameter. If the Sun were a sphere the height of a 12-story building, a neutron star with the same mass would be smaller than a grain of sand. The density at the center of a neutron star is roughly 1 billion metric tons per cubic centimeter. If you could somehow extract a cubic centimeter of material from the center and bring it to Earth, that tiny cube would weigh more than every large ship ever constructed by humanity combined. If you placed it on the ground, it would immediately sink through the surface. Not because the ground is weak, but because no material on Earth can support a billion metric tons concentrated on a surface area of 1 square centimeter. The sample would punch through rock, through the mantle, all the way to the center of the Earth, where it would oscillate back and forth, eventually settling at the core. 1 cubic centimeter of neutron star material is denser than the entire Earth. We've already encountered the staggering surface conditions: gravity 200 billion times Earth's, escape velocity a third the speed of light. But to put those numbers in human terms, a person weighing 70 kilograms on Earth would weigh about 14 trillion kilograms on a neutron star. That's not a meaningful weight. That's annihilation. No human, no spacecraft, no material ever created could survive even a distant approach. The gravitational environment of a neutron star is not merely hostile. It is incompatible with the existence of anything built from ordinary matter. Neutron stars rotate incredibly fast, and the reason for this is simple physics: conservation of angular momentum. When the original star's core collapses from the size of Earth to the size of a city, angular momentum must be conserved. Angular momentum depends on mass, rotation speed, and the distribution of mass relative to the rotation axis. If you reduce the radius dramatically while keeping the mass roughly constant, the rotation speed must increase enormously to compensate. This is the same principle that explains why an ice skater spins faster when she pulls in her arms. The arms move closer to the axis of rotation, reducing the moment of inertia, and the rotation rate increases proportionally. For a neutron star, the collapse reduces the radius by a factor of roughly 50,000 compared to the original stellar core. The rotation rate increases by approximately the square of that factor. A star that was rotating once every few weeks can produce a neutron star that rotates many times per second. Newly born neutron stars can spin at rates up to several hundred rotations per second. Over time, they slow down gradually as they radiate energy through their magnetic fields. But some neutron stars in binary systems are spun back up by accreting matter from a companion star. The infalling matter carries angular momentum, which is transferred to the neutron star, increasing its spin. These recycled pulsars, called millisecond pulsars, are the fastest rotating neutron stars known. The current record holder is PSRJ 1748-2446 AD, which rotates 716 times every second. 716 complete revolutions per second. A point on its equator is moving at roughly 24% the speed of light. If this neutron star were somehow placed where our sun is, a point on its equator would be circling at about 70,000 kilometers per second. It would complete a full revolution faster than it takes a hummingbird to beat its wings once. The precision of pulsar rotation is extraordinary. Some millisecond pulsars are so stable that their pulse arrival times can be predicted to within a few hundred nanoseconds over periods of years. They are natural clocks of incredible accuracy, rivaling the best atomic clocks on Earth. This precision has made pulsars invaluable for testing fundamental physics. In 1974, Russell Hulse and Joseph Taylor discovered a binary pulsar system, two neutron stars orbiting each other. By carefully timing the pulsars over years, they were able to measure the orbital decay of the system. The orbit was shrinking at exactly the rate predicted by Einstein's general relativity if the system were losing energy by emitting gravitational waves. This was the first indirect detection of gravitational waves, decades before LIGO's direct detection in 2015, and it earned Hulse and Taylor the Nobel Prize in Physics in 1993. Neutron stars also have extraordinarily powerful magnetic fields. A typical neutron star has a magnetic field of about 100 million to 1 trillion Tesla. Earth's magnetic field, by comparison, is about 0.00005 Tesla. So a typical neutron star's magnetic field is roughly 1 trillion times stronger than Earth's. But some neutron stars, called magnetars, have fields that are even more extreme. A magnetar can have a magnetic field of about 100 billion to 100 trillion Tesla. These are the strongest magnetic fields known to exist anywhere in the universe. At these field strengths, bizarre things happen. The vacuum of space itself becomes birefringent, meaning it bends light differently depending on the light's polarization, an effect predicted by quantum electrodynamics, but incredibly difficult to observe under normal conditions. Atoms are distorted from their normal spherical shapes into elongated cylindrical structures aligned with the magnetic field. The electron orbitals, instead of forming spherical shells, are compressed into tight cylinders. Chemistry as we know it ceases to exist. The energy levels of atoms are completely rearranged. Even the properties of empty space are altered. In 2017, astronomers using the European Southern Observatory's Very Large Telescope observed signs of vacuum birefringence in light from a neutron star for the first time, confirming a prediction of quantum electrodynamics that had been waiting for experimental verification for over 80 years. Magnetars are also responsible for some of the most violent events in the universe. They produce enormous bursts of X-rays and gamma rays when their crusts crack under the stress of the magnetic field. The magnetic field exerts tremendous forces on the solid crust, and as the field evolves over time, these forces build up until the crust fractures. The resulting starquake releases a burst of energy that can be detected across the galaxy. On December 27, 2004, a magnetar designated SGR 1806-20, located about 50,000 light years from Earth on the far side of our galaxy, produced a giant flare so powerful that it briefly outshone every other X-ray source in the sky combined. The gamma-ray flash lasted about 0.2 of a second and released as much energy as the Sun produces in about 250,000 years. From 50,000 light years away, this burst of energy was intense enough to measurably ionize Earth's upper atmosphere and disrupt some satellite communications. A flash of energy from a neutron star smaller than the city on the other side of the Milky Way, affecting our planet's atmosphere. That's the power stored in a magnetar's magnetic field. Pulsars provide perhaps the most compelling direct evidence that neutron stars exist and have the properties we've described. A pulsar is a neutron star whose magnetic axis is tilted relative to its rotation axis. As the neutron star rotates, its magnetic poles sweep across the sky like the beams of a lighthouse, charged. Particles accelerated along the magnetic field lines near the poles emit intense beams of radiation, primarily radio waves, but sometimes X-rays and gamma rays as well. If Earth happens to lie in the path of one of these beams, we see a regular pulse of radiation each time the beam sweeps past us. The period of the pulses equals the rotation period of the neutron star. The first pulsar was discovered in 1967 by Jocelyn Bell Burnell, a graduate student at Cambridge University working under the supervision of Anthony Hewish. Bell Burnell noticed a strange, incredibly regular signal in her radio telescope data. The signal pulsed with a period of about 1.337 seconds, repeating with a regularity that seemed almost artificial. The signal was so precise and so unexpected that Bell Burnell and Hewish initially considered the possibility that it might be a signal from an extraterrestrial civilization. They half-jokingly designated the source LGM-1 for Little Green Men 1, but they quickly discovered additional pulsing sources in other parts of the sky, which made the extraterrestrial hypothesis unlikely. If it were aliens, they'd have to be in multiple locations, all sending the same kind of signal. The explanation was natural. These were rotating neutron stars, objects that had been predicted theoretically but never observed until that moment. Today, more than 3,400 pulsars have been discovered. Their periods range from about 1.4 milliseconds for the fastest millisecond pulsars to about 23 seconds for the slowest known pulsars. The diversity of pulsar behavior is extraordinary. Some are solitary, spinning down gradually as they lose energy. Some are in binary systems, orbiting companion stars. Some are accreting matter, being spun up by the infalling material. Some produce only radio waves. Some emit X-rays or gamma rays. Some exhibit sudden glitches in their rotation. Some show gradual changes in their pulse profiles over time. Each pulsar is a laboratory for extreme physics, testing our understanding of matter, gravity, and electromagnetism under conditions we could never reproduce on Earth. The equilibrium inside a neutron star is remarkably stable. Once formed, a neutron star maintains its structure for an almost unfathomably long time. It cools gradually, radiating away its residual heat. A newly formed neutron star might have internal temperatures of hundreds of billions of degrees, but it cools rapidly in its first million years or so, primarily by emitting neutrinos from its interior. After about a million years, the interior temperature drops to a few 100 million degrees, and the dominant cooling mechanism shifts to photon emission from the surface. Over billions of years, the neutron star continues to cool, becoming progressively dimmer. Eventually, it will become too cold and faint to detect with any current technology. But throughout this entire cooling process, the neutron star never collapses. The degeneracy pressure and nuclear forces that hold it up don't depend on temperature. The neutron star at 1 billion years old, cold and dim, is just as structurally sound as the day it formed, blazing with heat from its violent birth. It will remain stable essentially forever, or at least for as long as the universe itself lasts. Neutron stars are permanent features of the cosmos, once created, never destroyed, unless something adds enough mass to push them past their limit. This is what makes neutron stars so extraordinary. They are the densest stable objects in the known universe. Unlike a black hole, which is a region of space-time where collapse has gone to completion, a neutron star has structure. It has layers. It has a crust and a core. It has quantifiable properties, a specific mass, radius, temperature, rotation rate, and magnetic field. It interacts with the universe around it. It can be observed, measured, and studied. It is the densest thing in the cosmos that still has an identity. A neutron star is the universe's answer to the question of how dense matter can become while still remaining matter. It's the last stand of structure against gravity, the final configuration that physics permits before matter ceases to exist as matter. Inside a neutron star, gravity and quantum mechanics are locked in a battle that has lasted for millions or billions of years, and neither side has won. Gravity pulls inward with a force that would crush any ordinary material to nothing. Quantum mechanics pushes outward with a pressure that arises from the deepest laws governing the behavior of particles. And the two forces balance exactly, creating an object that is simultaneously the most extreme and the most stable thing in the known cosmos. But that balance is not infinitely strong. It cannot resist any amount of gravity. There is a point, a specific mass threshold, beyond which even neutron degeneracy, pressure, and the nuclear force combined cannot hold. Beyond which the quantum stubbornness of fermions, the force that built the periodic table and holds up white dwarfs and sustains the densest stars in the universe, finally meets a gravitational force it cannot match. And when that threshold is crossed, the consequences are absolute and irreversible. This brings us to the edge of the story, the point where the neutron star fails, the point where gravity finally wins. In 1939, two physicists published a paper that would define the boundary between neutron stars and black holes forever. Their names were J. Robert Oppenheimer and George Volkoff. Oppenheimer would later become famous for an entirely different reason. As the lead scientist of the Manhattan Project, the effort that produced the first nuclear weapons during the Second World War. But in 1939, Oppenheimer was a theoretical physicist at the University of California, Berkeley, working on problems in astrophysics. Volkoff was a Canadian physicist who had studied under Oppenheimer and collaborated with him on problems involving the structure of extremely dense matter. Building on earlier mathematical work by the American physicist Richard Tolman, Oppenheimer and Volkoff used Einstein's general theory of relativity to calculate the maximum mass that a neutron star could possess before collapsing into something else entirely. That maximum mass is now called the Tolman-Oppenheimer-Volkoff limit, or the TOV limit, and it represents one of the sharpest boundaries in all of physics. Below this limit, matter survives. Above it, matter is destroyed. The calculation that Oppenheimer and Volkoff performed was groundbreaking because they recognized something crucial. Something that changes everything about how gravity works at these extremes. At the densities and gravitational field strengths found inside a neutron star, Newtonian gravity is no longer adequate. Isaac Newton's law of gravitation, the framework that beautifully describes the motion of planets, the trajectories of rockets, the orbits of satellites, and virtually every gravitational phenomenon we encounter in everyday life, breaks down when gravity becomes this strong. You need Einstein's general theory of relativity to describe gravity accurately in these conditions. And general relativity makes gravity harder to resist, not easier, harder. Here's why, and this is one of the most counterintuitive and devastating results in all of theoretical physics. In Newtonian gravity, the gravitational force depends only on mass. The more mass you have, the stronger the gravitational pull. Simple, straightforward. And in Newtonian gravity, pressure is purely helpful. Pressure pushes outward, resisting gravity. If you could generate enough pressure, you could, in principle, support any amount of mass against gravitational collapse. There's no upper limit in Newtonian physics to the mass you can hold up, as long as you have enough pressure. But Einstein's general relativity tells a different story. In general relativity, gravity isn't just caused by mass, it's caused by energy and momentum in all their forms. And pressure is a form of energy. Pressure contributes to the gravitational field. Let me say that again because it's the key to understanding why neutron stars have a maximum mass. In general relativity, pressure generates gravity. Pressure, the very thing that's supposed to resist gravitational collapse, also adds to the gravitational force causing the collapse. This creates a feedback loop that doesn't exist in Newtonian physics. And it's this feedback loop that ultimately dooms matter above a certain mass. Think about what happens as a neutron star becomes more massive. Gravity becomes stronger. To resist this stronger gravity, the matter must develop higher pressure. The neutrons are squeezed into higher energy states. The nuclear force is pushed harder. The degeneracy pressure increases, and the pressure does increase, and it does resist gravity up to a point. But in general relativity, that increased pressure also contributes to the gravitational field. It makes gravity stronger, which means the matter needs even more pressure to resist, which adds even more to the gravitational field, which requires even more pressure. Each increment of pressure that tries to save the star simultaneously strengthens the force that's trying to destroy it. At low masses, this effect is small. The pressure contributes only a tiny amount to the total gravitational field compared to the contribution from mass alone. The feedback loop exists, but it's weak. Gravity and pressure can still find a balance, and the neutron star stabilizes. But as the mass increases, the effect becomes more pronounced. The pressure required to support the star becomes enormous, and the gravitational contribution of that pressure becomes significant. The feedback loop gets stronger and stronger. You need more pressure to support the star, but more pressure makes the star harder to support. Beyond a certain mass, the feedback loop becomes self-defeating. The pressure required to hold up the star is so immense that its gravitational contribution exceeds the support it provides. More pressure makes things worse, not better. There is no equilibrium solution. No amount of pressure can support the star, because any pressure you add creates more gravity than it counteracts. This is the Tolman-Oppenheimer-Volkoff limit. It's the mass at which the general relativistic feedback between pressure and gravity becomes insurmountable. Below this mass, quantum degeneracy pressure and the nuclear force can hold the star up. Above this mass, they cannot. Not because they become weaker, not because they stop working, but because the very act of resisting gravity strengthens gravity beyond what resistance can overcome. This is a uniquely relativistic effect. It has absolutely no analogue in Newtonian physics. In Newton's universe, there would be no maximum mass for neutron stars. You could always find enough pressure to balance any amount of gravity because pressure doesn't contribute to gravity in Newtonian theory. It was only when Oppenheimer and Volkoff applied Einstein's equations, the equations of general relativity, to the problem that the maximum mass emerged. General relativity turns pressure, the defender, into a traitor. The very force that holds the star up is also feeding the force that tears it down. And above a critical mass, the betrayal becomes total. Oppenheimer and Volkoff's original calculation used a simplified model. They treated the neutrons as an ideal gas of free particles that didn't interact with each other. No nuclear force, no complex interactions, just pure neutron degeneracy pressure resisting gravity within the framework of general relativity. This simple model gave a maximum mass of about 0.7 solar masses. This was actually lower than the Chandrasekhar limit for white dwarfs, which immediately told them the model was too simplistic. Real neutrons interact with each other through the strong nuclear force, and these interactions, particularly the repulsive core at short distances, significantly stiffen the equation of state and increase the pressure at high densities. When you include the nuclear force, the TOV limit increases substantially. Modern calculations using sophisticated models of nuclear interactions informed by decades of experimental nuclear physics and theoretical developments place the TOV limit somewhere between about 2 and 3 solar masses. The exact value remains uncertain because it depends on the equation of state of ultra-dense matter, which we still don't fully understand. As we discussed, different theoretical models of nuclear interactions produce different equations of state. and a stiffer equation of state permits a higher maximum mass. The true TOV limit is somewhere in this range, and pinning it down precisely requires understanding the behavior of matter under conditions that no earthly laboratory can reproduce. But observations have been steadily narrowing the possibilities. The most massive neutron stars that have been reliably measured provide a hard lower bound on the TOV limit. If a neutron star has been observed with a mass of 2.35 solar masses, then the TOV limit must be at least 2.35 solar masses. That star exists. It hasn't collapsed. Therefore, the physics must allow it. Several neutron stars have now been measured with masses around or above 2 solar masses. PSRJ 0348 plus 0432, measured through precise timing of its orbital motion with a white dwarf companion, has a mass of about 2.01 solar masses. PSRJ 0740 plus 6620, measured using a similar technique called Shapiro delay, has a mass of about 2.08 solar masses. And PSRJ 0952-0607, a rapidly spinning millisecond pulsar whose mass was determined through observations of its companion star, comes in at approximately 2.35 solar masses, making it one of the heaviest neutron stars confirmed to date. Each of these measurements eliminates softer equations of state that would predict maximum masses below these values. The physics must be stiff enough to support these stars. From the other direction, observations of black holes provide constraints on where the TOV limit sits from above. The lightest stellar mass black holes that have been confidently measured have masses of about 5 solar masses. For years, there appeared to be a gap between the heaviest neutron stars, around 2 to 2.5 solar masses, and the lightest black holes, around 5 solar masses. This mass gap in the range of roughly 2.5 to 5 solar masses was puzzling. Were there simply no compact objects in this mass range? Or were they there but hard to detect? The existence of this gap, if real, would tell us something important about how supernovae produce compact remnants. Perhaps the explosion mechanism naturally produces either neutron stars below about 2.5 solar masses, or black holes above about 5 solar masses, with nothing in between. Gravitational wave astronomy has begun to probe this question directly, and its contributions to our understanding of the TOV limit have been nothing short of revolutionary. On August 17th, 2017, the LIGO and Virgo gravitational wave detectors recorded an event that would become one of the most important observations in the history of astrophysics. The event was designated GW170817, and it was the gravitational wave signal from 2 neutron stars spiraling toward each other and merging. This was the first time gravitational waves from a neutron star collision had ever been detected. But what made GW170817 truly extraordinary was that it was also observed in electromagnetic radiation. Gamma-ray telescopes detected a short gamma ray burst arriving 1.7 seconds after the gravitational wave signal. Over the following days and weeks, telescopes across the entire electromagnetic spectrum, from radio waves through infrared, visible light, ultraviolet, X-rays, and gamma rays, observed the aftermath. The event was observed by over 70 observatories on every continent and in space. It was the most thoroughly observed astrophysical event in history. The gravitational wave signal told physicists the masses of the two neutron stars. They were about 1.46 and 1.27 solar masses, for a total of roughly 2.73 solar masses. The signal also contained information about the neutron star's internal structure, encoded in how they deformed each other gravitationally during the final moments of the inspiral. This tidal deformation depends on the equation of state. A stiffer equation of state makes the neutron stars larger and more easily deformed. A softer equation of state makes them smaller and more compact. By analyzing the gravitational wave signal, physicists were able to constrain the equation of state more tightly than ever before. But the most dramatic information came from what happened after the merger. The two neutron stars, with their combined mass of about 2.73 solar masses, merged into a single object. For a brief moment, this object existed as what physicists call a hypermassive neutron star. A neutron star whose mass exceeds the TOV limit, but which is temporarily supported by rapid differential rotation and thermal pressure from the violent merger. This state cannot last. The differential rotation dissipates, the thermal pressure fades, and the object must either settle down to a stable neutron star if its mass is below the TOV limit, or collapse into a black hole if its mass is above it. The electromagnetic observations strongly suggest that the remnant of GW170817 collapsed into a black hole within about 1 second of the merger. The short gamma-ray burst is thought to be powered by the formation of a black hole and the launch of relativistic jets. The properties of the subsequent electromagnetic emission, called a kilonova, are also consistent with black hole formation. This tells us something crucial. The combined mass of 2.73 solar masses was above the TOV limit. After the merger, after the temporary support from rotation and thermal pressure dissipated, the remnant could not sustain itself. It collapsed. This places an upper constraint on the TOV limit. It must be below roughly 2.73 solar masses, accounting for some mass that was ejected during the merger, and some energy radiated away as gravitational waves. Detailed analyses place the constraint at roughly 2.2 to 2.3 solar masses. Combined with the lower bound from the most massive known neutron stars, this pins the TOV limit to a surprisingly narrow range, somewhere around 2.2 to 2.4 solar masses, give or take uncertainties in the nuclear physics. In 2019, LIGO and Virgo detected another event, GW190814, that added intrigue to this picture. This event involved the merger of a black hole of about 23 solar masses with a compact object of about 2.6 solar masses. That secondary object fell squarely in the mass gap between neutron stars and black holes. Scientists still debate what it was. If it was a neutron star, it would be by far the most massive ever detected, pushing the TOV limit higher than most models predict. If it was a black hole, it would be the lightest stellar mass black hole ever observed, and the mass gap would be partially filled. The gravitational wave signal alone couldn't distinguish between a neutron star and a black hole for the secondary object. No electromagnetic counterpart was detected, which might favor the black hole interpretation, since a neutron star merging with a black hole can, in some cases, produce observable electromagnetic emission. But the absence of electromagnetic emission isn't conclusive. The debate continues, and this single ambiguous event illustrates how much we still have to learn about the boundary between neutron stars and black holes. So, what actually happens when a neutron star exceeds the TOV limit? What does the collapse look like? The details depend on how the mass is accumulated. If a neutron star in a binary system is slowly pulling matter from a companion star, the process is gradual. Matter spirals inward, accumulates on the neutron star's surface, and increases the total mass bit by bit. As the mass approaches the TOV limit, the star contracts slightly. The central density increases. The pressure increases, but so does the gravitational contribution of that pressure. The star becomes more compact, denser, closer to the edge of stability. When the mass crosses the threshold, the collapse begins. And once it begins, nothing in the known laws of physics can stop it. The general relativistic feedback loop takes over completely. Pressure increases gravity faster than it supports against gravity. The core contracts, which increases the density, which requires more pressure, which adds more gravity, which drives more contraction. The process is a runaway. It accelerates. It feeds on itself. The entire interior of the neutron star collapses on a timescale of milliseconds. The matter falls inward at a significant fraction of the speed of light. As the matter compresses beyond the point of no return, space-time itself is warped beyond recognition. The gravitational field becomes so extreme that the curvature of space-time closes in on itself. An event horizon forms. This is a boundary in space-time, not a physical surface, not a wall or a barrier made of material, but a mathematical boundary defined by the geometry of space-time itself. Inside the event horizon, all paths through space-time point inward. Every possible trajectory, even one traveling at the speed of light, leads toward the center. Nothing can move outward, nothing can escape. Light emitted inside the event horizon curves back inward. Information generated inside the horizon can never reach the outside. The interior is causally disconnected from the rest of the universe. Whatever happens inside the event horizon stays inside the event horizon. Permanently. Irreversibly. The matter that once constituted the neutron star, the trillions upon trillions of neutrons that were so stubbornly resisting compression, the quantum degeneracy pressure that held the star up for millions of years, all of it is now inside the event horizon and falling toward the center. General relativity predicts that this collapse continues all the way to a singularity, a point of theoretically infinite density where the known laws of physics break down entirely. Whether a true singularity actually forms, or whether some unknown physics intervenes at the smallest scales, is one of the deepest unsolved problems in theoretical physics. Quantum gravity, a theory that would unify general relativity with quantum mechanics, is expected to resolve this question. But no complete, experimentally confirmed theory of quantum gravity exists yet. String theory, loop quantum gravity, and several other approaches have been proposed, but none has been verified. What remains after the collapse is a black hole, an object defined entirely by three numbers: its mass, its electric charge, and its angular momentum, its spin. Everything else about the original neutron star, its composition, its temperature, its internal structure, its magnetic field configuration, its history, all of that information is hidden behind the event horizon, inaccessible to the outside universe. This is described by the no-hair theorem, which states that a black hole is completely characterized by just those three quantities. Two black holes with the same mass, charge, and spin are identical, regardless of how they formed. A black hole formed from the collapse of a neutron star is indistinguishable from a black hole of the same mass formed from any other process. The transition from neutron star to black hole is a transition from something to nothing. Not literally nothing, because the mass and gravity are still there, but nothing in the sense of structure. A neutron star has layers, composition, temperature, density profiles, magnetic fields, rotation quarks, observable properties. A black hole has none of these. It's featureless, smooth, described by three numbers and nothing more. The rich internal physics of the neutron star, the superfluid neutrons, the superconducting protons, the possible quark matter in the core, the crystalline crust, all of it is erased, replaced by geometry, pure curved space-time with no material content visible to the outside universe. The existence of the TOV limit tells us something profound about the deepest relationship between the two great pillars of modern physics, quantum mechanics and general relativity. These two theories are extraordinarily successful within their own domains. Quantum mechanics describes the subatomic world with breathtaking precision. General relativity describes gravity and the large-scale structure of space-time with equal precision, but they are fundamentally incompatible in their current forms. They use different mathematical frameworks. They make different assumptions about the nature of reality. They disagree about whether space-time is smooth or granular, whether gravity is a force or a geometric property, whether information can be destroyed. The neutron star sits precisely at the intersection of these two theories. It's the place where quantum mechanics and gravity meet on nearly equal terms. Below the TOV limit, quantum mechanics has the upper hand. The Pauli exclusion principle dictates the structure. Degeneracy pressure holds gravity at bay. The fermions win. Above the TOV limit, general relativity takes over. The relativistic pressure-gravity feedback overwhelms quantum resistance. Space-time curvature dominates, gravity wins. The TOV limit itself is the boundary line, the exact point where neither theory dominates, where the two most fundamental descriptions of nature are perfectly matched. And understanding what happens exactly at this boundary, where quantum effects and gravitational effects are equally important, may require the very theory that physicists have been seeking for a century. A unified theory of quantum gravity. Every neutron star in the universe is a testament to the power of quantum mechanics on cosmic scales. Every black hole is a testament to the dominance of gravity when mass exceeds the quantum threshold. And the boundary between them, defined by the TOV limit, is written into the laws of physics as firmly as the speed of light or the charge of an electron. It's not a technological limitation. It's not an engineering challenge. It's a fundamental law of nature. No civilization in the universe, no matter how advanced, no matter how many billions of years they've had to develop technology, can build a stable neutron star heavier than the TOV limit. They can't reinforce the degeneracy pressure. They can't turn off the general relativistic feedback. The universe doesn't permit it. Think about what we've discovered on this journey. We started with a massive star burning through its nuclear fuel, building up an iron core that can no longer sustain itself. We watched that core collapse in less than a second. converting its matter into neutrons, producing one of the most violent explosions in the cosmos. We descended into the quantum world to understand the Pauli exclusion principle, the law that forbids identical fermions from sharing quantum states. We saw how this principle creates degeneracy pressure, a force that doesn't depend on temperature, that persists even at absolute zero, that arises purely from the mathematical structure of quantum mechanics. We trace this pressure from atoms to white dwarfs to neutron stars, watching the same principle operate at progressively more extreme scales. We explored the interior of a neutron star, from its crystalline crust through the neutron drip line into the superfluid core and the unknown exotic matter at the very center. And finally, we arrived at the TOV limit, the point where general relativity turns the neutron star's own pressure against it, where the feedback between pressure and gravity becomes inescapable, and the collapse into a black hole becomes inevitable. The answer to why neutron stars don't collapse is both simple and profound. They don't collapse because the neutrons inside them are fermions. Fermions obey the Pauli exclusion principle. The Pauli exclusion principle creates a degeneracy pressure that resists compression regardless of temperature. This pressure, supplemented by the repulsive nuclear force at short distances, balances gravity and holds the star in equilibrium. But this balance has a limit. Beyond roughly 2 to 2.5 solar masses, general relativity turns the star's own pressure into its executioner. A black hole forms, and the matter that fought so valiantly against gravity vanishes behind an event horizon, removed from the observable universe forever. The same quantum principle that makes the ground solid beneath your feet is what prevents a dead star from becoming a black hole. The same force that gives atoms their structure, that creates the diversity of chemical elements, that makes life and consciousness possible, is the force that holds up the densest stable objects in the known universe. And the failure of that force, when gravity becomes too strong, creates the most mysterious objects in existence. Objects where our understanding of physics breaks down, where matter ceases to be matter, where space-time curves back on itself and swallows everything, including light. Every time a pulsar flashes in the night sky, it's broadcasting proof that quantum mechanics can defeat gravity. Every pulse of radio light from a spinning neutron star is evidence that the Pauli exclusion principle works. That fermions really do refuse to share quantum states. That this refusal generates enough pressure to hold up a solar mass at nuclear density. It's a signal from the frontier of physics, from the densest stable matter in the universe, telling us that the quantum world and the gravitational world are locked in a balance that has persisted for longer than our species has existed. And somewhere out there right now, a neutron star is accumulating mass. Maybe it's in a binary system, slowly pulling gas from a companion star. Maybe two neutron stars are spiraling toward each other, drawing closer year by year, destined to merge in a cataclysm that will shake the fabric of space-time itself. Somewhere, the balance is shifting. The mass is climbing. The density at the center is increasing. The general relativistic feedback is growing stronger. And when it crosses that threshold, in a moment faster than the blink of an eye, the quantum pressure that held the star together for millions of years will fail. The neutrons that resisted gravity with every quantum state available to them will lose. The fermions that refuse to be identical will be crushed into a singularity where identity has no meaning. And a black hole will appear in the darkness, where a neutron star once stood. That boundary between survival and annihilation, between neutron star and black hole, is one of the sharpest edges in nature. It separates a universe where matter can exist from a universe where it cannot. It's defined by the interplay of quantum mechanics and general relativity, two theories that don't agree with each other, that haven't been unified, that still hold secrets we haven't uncovered. The neutron star sits on that edge, the last gasp of matter, the final structure that physics permits, the densest thing in the cosmos that can still be called a thing. And that is why neutron stars don't collapse, until they do. Thank you for joining me on this journey. If you found this exploration valuable, a like or subscribe would mean a lot. It helps me keep making these deep explorations of the cosmos. And the next time you look up at the stars, remember that some of those points of light are not ordinary stars at all. Some are the spinning remnants of dead ones, neutron stars, city-sized balls of quantum matter held together by the stubbornness of fermions that refuse to be identical. They've been winning the fight against gravity for millions of years. And on some quiet night, when the conditions are right and the mass tips just past the limit, one of them will finally lose. Good night. And may you never look at the stars the same way again.